Hi everyone, welcome to JEE MAX Mains Advanced Extreme series. This is season 2 and lesson 1 of complex numbers. So far in season 1, we have successfully completed some of the beautiful topics which are very useful for mains and advanced. Now, this is about the complete total discussion and thorough information on the chapter complex numbers, which play a very good role in all competitive examinations, including board examination. And actually, before this, you just watch our video. There I have given the basic introduction of the complex numbers history. Through that, you will get an idea about other real numbers and the numbers beyond the real numbers. Once after watching that complete video, then we will concentrate the analytical approach of the complex numbers in our season 2 classes. First, you please watch that particular video. Okay, my friends? And if you like that, you please share and subscribe our channel. And please don't forget to check the description. There I am providing every information for you. Now, with that, I will give the next best information about the complex numbers, the entire chapter with the theoretical as well as problem support. Okay, my friends, first watch the video. Thank you.
We arrived at an incredibly powerful tool in mathematics, science, and engineering, the complex plane. The complex plane is an extension of the number line where we include the imaginary dimension vertically. Just as we can plot xy coordinates on the xy plane, we can plot complex numbers on the complex plane. This arrangement is why Gauss preferred the term lateral over imaginary and inverse instead of negative. Gauss suggested that we should call the numbers to the right of the origin direct, the numbers to the left of the origin inverse, and the numbers above and below the origin lateral. Now that we've seen the complex plane, let's discuss why it's so powerful. We've seen two-dimensional planes before, where each axis represents a different quantity. In fact, we started our whole conversation with one. In a normal xy plane, there's no required connection between the dimensions, no rules about how they should relate to each other. On the complex plane, however, we have the rules of algebra with complex numbers we discussed earlier. These rules impose a very specific and useful relationship between the two dimensions. The first rule is how complex numbers add and subtract. The real and imaginary parts add independently, making complex numbers and the complex plane useful for problems involving motion in two dimensions. If we travel in one direction for a certain distance, and then in another direction, we can add the components of each part of our trip together to find the total distance we have traveled in each direction. So that's cool, but as you may already know, we can do the same exact thing with vectors. Where complex numbers get really interesting is through multiplication. We can multiply complex numbers together by FOILing, just as we do with binomials in algebra, with the minor complication that we know I squared can be replaced with -1. This is a perfectly valid algebraic solution to our problem, but is only half the picture. There is another equally valid way to think about multiplying complex numbers, and it has everything to do with the complex plane. Instead of just telling you what this interpretation is, it'll be way more fun to try to figure it out with some examples. To discover this deeper meaning for yourself, all you need to know is the following: how to multiply complex numbers algebraically as we just did, how to plot numbers on the complex plane, the Pythagorean theorem, and finally how to use arctangent to find angles. What's cool here is that if you're able to figure this out, you'll have discovered for yourself a super useful bit of math that was unknown to the smartest mathematicians on the planet until only 2 centuries ago. Next time, we'll uncover this interpretation of complex multiplication using the complex plane, and we're going to do it with 4 examples. 4 plus 3i times I, 4 plus 3i times 2i, 4 plus 3i times itself, and finally 2 plus I times 1 plus 2i. Through considering each of these problems on the complex plane and looking at the patterns that naturally emerge, we'll arrive at the deeper meaning we're searching for. Do try this at home. You'll find a link below to the problem statement on the Welch Labs blog. Even if you're already a boss at complex numbers, or if you have no idea what I'm talking about, I promise it's a valuable process. And we'll sort out all the details next time. Last time, we left off with a real math problem. What is the connection between complex multiplication and the complex plane? To get to the bottom of this, we'll use the 4 examples we mentioned last time. For each example, we'll plot the 2 numbers we're multiplying together. We'll also compute the result algebraically and add it to each plot. Our job now is to look for patterns. Back in part 5, we learned that I has something to do with rotation on the complex plane. So a good thing to keep track of here will be the angle our complex numbers make with the real axis. We can determine our angles using a little trigonometry, specifically the arctangent function. Now let's look for a connection between our 3 angles. After a little pondering, we see that the angle of the result is exactly equal to the angles of the numbers we're multiplying added together. This is the first half of the connection we're looking for. When multiplying on the complex plane, the angle of our result is equal to the sum of the angles of the numbers we're multiplying. Let's now have a closer look at our first 2 examples. Notice that the angles are identical, but the resulting complex numbers are not. This means that just keeping track of angles alone is not enough to sufficiently describe complex multiplication in the complex plane. There is something else going on. So what is the difference between these examples? It looks like multiplying by 2i has pushed our result further from the origin than multiplying by I. A good follow-up question is, how much further? We can measure the distance between the origin and our complex numbers by forming right triangles and using the Pythagorean theorem. Just as before, let's compute our measurement for each example and look for patterns. After some more pondering, we see that if we multiply our distances, we obtain the distance from the origin of the result. We now have the complete picture. When we multiply complex numbers on the complex plane, their angles from the real axis add, and their distances from the origin multiply. This is the connection we were looking for between complex multiplication and the complex plane. We now have completely separate, but completely equivalent interpretations of complex multiplication. To multiply 2 complex numbers together, we can follow the rules of algebra, or we can find each number's distance from the origin and angle to the real axis on the complex plane, and multiply and add each. And what's really cool here is that although these approaches look and are totally different, they do the same exact thing. What we're seeing here is the same underlying process from 2 separate vantage points. I really like this idea because it reminds me that there's more to math than what we see on the page. There are deeper truths embedded in our universe, and math is one way of expressing them. Now that we've made our discovery, let's formalize our results a bit. We found that the quantities we should keep track of when multiplying complex numbers on the complex plane are the distance from the origin and the angle from the real axis. These quantities turn out to be so important that we use them as another way to write complex numbers. Instead of writing complex numbers as the sum of their real and imaginary parts, we instead write them as their distance from the origin and the angle they make with the real axis. This is called polar form, and the distance from the origin gets a special name, magnitude. Multiplying complex numbers in polar form is super easy. We just multiply the magnitudes and add the angles. Division is pretty simple too, especially compared to dividing in rectangular form. To divide in polar form, we divide the magnitudes and subtract our angles. Next time, we'll show that this discovery is not only cool, but useful. Let's solve a simple equation. X cubed is equal to 1. What value of x would make this equation work? If you said x equals 1, way to go. 1 cubed is 1, we have found an answer. Now, are there any more answers? Back in part 1, we introduced the fundamental theorem of algebra, which says that a polynomial must have as many roots as its highest power. We can rearrange our equation as x cubed minus 1 is equal to 0 to make it a more obvious polynomial, and since our highest power is 3, this equation must have 3 solutions. There is an algebraic way to find all three answers, but it involves perfect cube factoring and the quadratic formula, and takes some work. Instead, let's try to solve the problem visually using the complex plane. Our question in words is what numbers, when multiplied by themselves 3 times, equal 1? Let's think about this problem using the polar form of complex numbers we discussed last time. We can think about 1 in the complex plane as the number with a magnitude of 1 and an angle of 0, or 360. When we multiply numbers in the complex domain, their magnitudes multiply and their angles add. Our result should have a magnitude of 1, and since 1 times 1 times 1 is 1, if we give each of our x's a magnitude of 1, our resulting magnitude will work out to 1. Easy. But what about our angles? We know that when multiplying complex numbers, our angles add, so we need an angle that when added together 3 times gives 0, or 360. 360 seems a little more reasonable, so what's the correct angle here? Since we're dividing 360 into 3 even parts, the right answer here is 360 divided by 3, or 120 degrees. When we put this together with the magnitude of 1, we have a second solution. It's the complex number with a magnitude of 1 and an angle of 120. This answer makes a lot of sense on the complex plane. Multiplying our answer by itself once results in a magnitude of 1 at an angle of 240 degrees, and multiplying by our answer again lands us exactly where we want it to be at a magnitude of 1 and an angle of 360 degrees, also known as the real number 1. This may seem like a strange answer for algebra class, so let's put it back in rectangular form. Our good friend the unit circle can save us some time here. We would like to know the rectangular coordinates of a point on the unit circle at an angle of 120 degrees. According to the unit circle, our answer is minus 1/2 for the real part and root 3 over 2 for the imaginary part. So now that we have an answer in rectangular form, let's try it. If we multiply out our result, we get 1. Pretty cool, right? We were able to solve a tough algebra problem visually using the complex plane, and get the same exact answer we obtained earlier through factoring. Finally, we've only found 2 answers so far, and the fundamental theorem of algebra demands that we have 3. We find our missing answer going the other way around the circle. If we start at minus 120 and multiply our number together 3 times, we also land at the purely real number 1. So our missing answer is negative 1/2 minus root 3 over 2i. So we found all the answers to our problem x cubed is equal to 1, and shown how the complex plane allows us to find these visually. In this case, using complex numbers saved us some time over the algebraic approach, and for more complicated problems, the complex plane becomes even more useful. For example, what if we changed the power in our original problem to 8? That is, x to the power of 8 minus 1 is equal to 0. We could try to factor this, or turn to our complex plane and see that just like our last problem, where we needed to divide the unit circle into 3 equal portions, we need to, in this case, divide our circle into 8 equal portions. So our solutions need to be at 45 degrees, again along the unit circle. All 8 answers, done. Next time, we'll show how imaginary numbers are the missing piece of the puzzle that make algebra complete. Before we finish up our series and solve our problem from part 1, let's talk about how complex numbers are the missing puzzle piece that make algebra complete. Back in part 1, we saw how the definition of what a number is has evolved over time, beginning with the natural numbers. The Egyptians figured out that these numbers were missing something, and it's pretty obvious today that the natural numbers are incomplete. However, as we saw with complex numbers, it's not always obvious when your numbers are missing something. Fortunately, there's a more sophisticated way to determine if we have all the types of numbers we need, the mathematical idea of closure. Let's play a game. I'll give you a set of numbers and an algebraic operation. I want you to tell me if any 2 numbers in the set, when combined with the operation, give a number that is not in the set. Our first set is the natural numbers, and our operation is addition. So the question is, are there any 2 natural numbers that when added together produce something that is not a natural number? After a little noodling, it should seem pretty reasonable that any 2 natural numbers added together result in another natural number. Mathematically, we can say that the set of natural numbers is closed under addition. Next, let's try the set of natural numbers and the operation of subtraction. For some pairs of natural numbers, like 6 and 4, things work out just fine. 6 minus 4 is 2, which is a natural number. But what about 4 minus 6? This results in an answer that is nowhere to be found in our set of natural numbers, so our set is not closed under subtraction. We need to expand our set to include 0 and negative numbers for this to be the case. So the set of natural numbers is not closed under subtraction, but the set of integers is. By expanding our number system, we can guarantee that any subtraction question we can ask will have an answer. As we include more algebraic operations, we must continue to expand our number system. Division requires us to expand our number system to include fractions, also known as rational numbers. Rational comes from the word ratio. Rational numbers are numbers that can be expressed as the ratio of two integers. Venn diagrams are pretty useful here because they help us visually express the idea that one set includes another. All integers are rational numbers because we can always express them as a ratio of two integers, but not all rational numbers are integers. Let's recap. So far, we've made it to the set of rational numbers, which includes numbers like 1, 0, minus 5, and minus 2/3. What operations are the rational numbers closed under? Well, any two rational numbers added together yield another rational number, so we can say that the rational numbers are closed under addition. We can say the same for subtraction, multiplication, and division. Now, what about powers and roots? Does a rational number raised to a rational power always yield a rational result? It turns out that for problems like 2/9 to the power of 2, this is no problem. Our result is rational. Where we get into trouble are problems like 2 to the power of 1/2. Raising something to the power of 1/2 is the same thing as taking the square root, so this is equivalent to the square root of 2. We'll save the full argument for another day, but it turns out that root 2 is not rational. There are no two integers that when divided equal exactly the square root of 2. Since numbers like this are not rational, we give them the name irrational. There's one more class of numbers that are even cooler than irrationals, the transcendental numbers like pi and e. We'll also save these for another day. So we've expanded our number system again to include irrationals, and all these numbers taken together form what we call the real numbers. Let's play our game one more time. Our set is now the real numbers, and our operation is taking roots. Do we have closure? Are there any real numbers that when we take some root yield a result that is not a real number? The answer is that despite all the types of numbers we've included along the way, we're still missing something. We can write an expression only using real numbers and roots, for example the square root of -9, that has no solution in the real numbers. For this problem to have an answer, we must expand our number system once more to include imaginary numbers. And taking all our real numbers from before, together with imaginary numbers, we arrive at our broadest class of numbers, the complex numbers. Initially, mathematicians were concerned that even complex numbers were not sufficient, that problems like the square root of -I would result in an even more complex number, perhaps even a three-dimensional number instead of our two-dimensional complex numbers. Fortunately, this turned out not to be the case. In fact, we can evaluate the square root of -I, again using our good friend the complex plane. Since -I has a magnitude of 1 and an angle of -90 degrees, we just need a number with a magnitude of 1 and an angle of -45 degrees. According to our unit circle, root 2 over 2 minus root 2 over 2i. So the square root of -I is just another complex number. There's no need for some wild new three-dimensional number. In fact, there's no operation in the world using addition, subtraction, multiplication, division, powers, and roots that the complex numbers can't handle. Imaginary numbers are the exact missing piece that makes algebra complete. So, what is this? We saw this shape back in part 1, and then proceeded to not talk about it for like 10 episodes. And at this point, I really wouldn't blame you if you thought this was some science fiction designed to get you excited about doing boring algebra problems. But before we chalk this up to unnecessary special effects, let's remember where this shape came from. We began our conversation in part 1 with an equation that appeared to have no solution, x squared plus 1 equals 0. And after all the work we've done so far, you can probably see how to find the answer algebraically. Subtract 1 from both sides of the equation and take the square root, resulting in x equals plus or minus I. Done. So that's cool, but to really make sense of our shape from part 1, we need to dig a little deeper and talk about functions of complex variables. The kinds of functions most of us are used to, functions of real numbers, have inputs and outputs that can be visualized using a single dimension. This means all our x values fit on a single number line, and so do our y values. It seems pretty reasonable then, that if we want to figure out how x and y are related, we should put our x number line facing one way on a piece of paper, and put our y number line on the same piece of paper, just facing the other way. This forms a two-dimensional grid known as the Cartesian coordinate system. Apparently invented by René Descartes in the 16th century after watching flies crawl around, the Cartesian coordinate system is a super powerful tool for understanding the relationship between two variables. The Cartesian coordinate system is powerful because it allows us to take abstract ideas like functions and turn them into something our brains can grasp much more intuitively: shapes. By giving each point on the plane its very own coordinates, Descartes was able to bring together the two largest areas of mathematics at the time: algebra and geometry. This greatly aided early efforts at classifying functions by Newton and others, and today the Cartesian coordinate system shows up everywhere, helping us do all kinds of things like spot trends in data. So that's all fun and wonderful, but the Cartesian coordinate system does come with a disclaimer: it only works in two dimensions. This limitation becomes a real problem when we start to think about functions of complex variables. These functions take in complex numbers for their inputs, and for the most part also output complex numbers. This means the numbers we put in and get out of our function no longer fit on number lines. We need two complex planes to keep track of our numbers, one for our input and one for our output. This raises an important question. If, when visualizing these functions, what we're really interested in is the connection between the input and output, how do we visualize what's happening on both planes simultaneously? We could try to fit our input and output planes together somehow, as we did with our number lines for real valued functions, but we quickly run into a pretty serious issue. As you likely know, the universe we live in has 3 spatial dimensions, so there's no way to fit the 4 spatial dimensions we need into a single structure that our brains can comprehend. We simply run out of dimensions. Fortunately, there are some very clever ways to see the relationship between two complex variables. But before we can get to these, we need to think about the mathematics of complex functions. Even though using separate planes for our input and output is not a perfect solution, this approach can still help get us started. Let's try it out with our original function, f of x equals x squared plus 1. Before we begin, let's make a quick variable change to make things easier down the road. We'll change the name of our input variable from x to z and call our output variable w. Since z and w each have a real and imaginary part, let's go one step further and give these parts names. We'll let z equal x plus iy, so x represents the real part of z, and y represents the imaginary part. We'll also let w equal u plus iv. Just as we can use tables to keep track of our inputs and outputs for real valued functions, we can also use tables to keep track of our inputs and outputs for complex functions. However, we now need 4 columns to keep track of our 4 variables, x, y, u, and v. We can now experiment with our function f of z equals z squared plus 1. If we plug in a complex number to our function, for example z equals 1 plus I, we can do a little algebra and obtain our result, w equals 1 plus 2i. Plotting our inputs and outputs, we see that the point 1 plus I in our input plane was pushed or mapped by our function to 1 plus 2i in our output plane. Let's plug in a few more points here and see if we can find a pattern. If we test points along a straight line in our input space, we see that in our output space, our straight line is transformed into a curved line. Interesting. As you can imagine, plugging in points like this can get pretty tedious. To speed things up, let's let a computer do it for us. And instead of having our computer just map certain points, let's have it map all the points. We'll take advantage of the fact that the image you're seeing is just a collection of pixels that happen to be arranged on a grid. We'll use some code written in the programming language Python to move every single pixel in our input space to its proper location in the output space. To make this work, we'll assign each pixel in our input video a complex number that corresponds to its location on the complex plane. We can then let our code take care of the tedious work of moving each pixel to its new location, as dictated by our function, z squared plus 1. Our code will move points exactly as we did by hand before. If we have a blue pixel at the 1 plus I location on our input graph, then this blue pixel will be moved to the 1 plus 2i location on our output graph, because f of 1 plus I is equal to 1 plus 2i. We saw before that our function warped a straight horizontal line into a curvy one, so it should have some interesting effects on our video. We'll include some reference markers on top of our input and output planes to keep track of our numbers, but we won't transform these pixels. Alright, ready? Let's start by drawing some simple lines. A horizontal line along the positive x-axis turns out to be something pretty similar in our output space. But what about a line along the positive imaginary axis? This line appears to have been rotated. As we add more lines, we begin to see a pattern. Our family of straight lines is turned into a family of curved lines. Cool, right? So we found one pattern, but how is this pattern explained by our function z squared plus 1? And more importantly, how does this fit with everything else we've learned about complex numbers? What else would be interesting to draw in our input space to test our mapping? What shape would you draw to learn more about what our function is doing? Next time, more shapes.